Hello and welcome to Explaining Rasterlizer series, a series where we try to understand how Rasterlizer works one subsystem at a time. So, what has been happening recently? First, we covered the syntax tree data structure. We wrote mini Rowan, then we looked at the real Rowan and understood how we can implement a data structure which can represent a syntactic tree which has an exact correspondence to the underlying text. After that, we have been looking into the parser, and the parser was curious in two interesting aspects. First of all, it was completely abstracted away from a particular syntax tree implementation, and second, it was like the IDE style error resilient parser. So today, I would like to finally look into how this all works together and how do we bridge that error resilient and abstract parser with a concrete Rowan based syntax tree. Before we start discussing that, I would like to briefly cover the two things we didn't, well, I would like to say about the two things we didn't cover in the parsing video lectures. First of all, I've glossed over expression parsing. Parsing expressions with recursive descent handwritten parser is rather complicated. You need a prod parser for that, and that is like pretty like it's not a complicated algorithm. It's like very short, but like conceptually it's pretty fun because it combines both recursion and iteration. So that's like the hard bit. We didn't cover it. We probably would record some extra lecture about it sometime in the future. I don't know. The second thing we didn't cover is incremental parsing. The parser we saw actually has a simple support for incrementality where it can only parse the smallest curly braced block around the edit, and again that's like not essential to understanding the basics of rationalizer, so can be covered separately. Okay, so without further ado, let's look at how we bring everything together. Let's open Rust Analyzer and look at the crates. So as a reminder, the parser lives in the parser crate. It doesn't know about syntax trees. Syntax tree implementation lives in the Rowan crate, and that crate is actually outside of Rasterlizer repository. The crate we'll be looking at today is syntax, and that is the real API which is used by the rest of Rust Analyzer. The rest of Rust Analyzer doesn't really touch the parser, it doesn't really touch Rowan, it works only with types and functions defined in the syntax. So syntax is again is a facade crate, and I really love this facade pattern, and we use it throughout Rust Analyzer to provide this like a cake of layers where each layer is better, but where each individual layer is pretty detangled from the rest of the thing. Okay, so the syntax crate is actually pretty big. It also contains a bunch of generated code, so it will take more than one lecture to cover it. And today we start with like the basics. So let's look at lib.rs. Yeah, as you see, there's like, and by the way, if you recall, we actually looked at this crate a while back. We were looking at this API walkthrough test, which showcases the syntax tree API we are able to build with all those separate pieces. So today we are finally starting to get to the meat of it. We covered all the nuts and bolts of underlying implementation, and today we will look at beginnings of like the actual API which this API walkthrough test uses. Okay, so the main module I think here is syntax node. So what this syntax node module defines is the specific syntax node and syntax token types which are used from Rowan. It's confusing, so let's see. If you recall, Rowan has API types which are parameterized over the language. And the role of the language is like a grand name, but really what language does is it just casts U16, which is like a Rowan syntax kind, which isn't language specific, to some better typed syntax kind to allow for better debug representation. So here we define Rust language, and we say that its syntax kind is the thing we saw in the parser, like this giant enum with all the different variants of syntax. Yeah, and it casts and it defines casts from the raw syntax, which is like pretty similar. I guess where they are defined. Yeah. So like to cast U16 to syntax kind, we just assert that U16 isn't too large and then just transmute. And yeah, kind of like this horrible, but sadly there isn't a nice built-in way in Rust to transfer from an integer to a fieldless enum. I think there is like some pull request in progress which adds this ability, which would be really welcome. And in the opposite direction, it's even easier. You just cast it via S. Okay. So yeah, Rust language, the definition of. Then using this Rust language, we define a bunch of type aliases for everything, and that's what gets used by the rest of Rust analyzer. So what, in terms of syntax, what we have been looking so far is private implementation detail, and you don't actually need to touch those things while you work on Rust analyzer. But these things are literally used like throughout the code. So yeah, I've just invoked find references, and we need. Yeah, that's actually interesting. So one problem here is that find references just takes a lot of time because Rust analyzer isn't yet as fast as it needs to be. And well, that's interesting. Actually, yeah, I'm surprised that we find references to this type aliases. I would expect this to not work, but it works. Okay, that's great. So yeah, if you can see like this is really a vocabulary type of Rust analyzer, and it's like used everywhere. And like this outlier with like 400 instances is actually generated code, which we'll probably be covering in the next lecture. Anyway, so a bunch of types. Syntax tree builder. That's a wrapper around Rowan's builder to build syntax trees. Validate block structure. Okay, I've just realized that like this extra validation will fail on a specific case I'm working on right now. Anyway, it's probably unrelated. So yeah, again, like standard pattern, we take some library type and we wrap it into API, which adds extra stuff on top. So nothing particularly interesting here. Well, I guess like the thing which this adds on top of Green Node Builder is ability to record syntax errors. As a reminder, some of the errors are recorded as explicit syntax node in the tree, like a node which contains erroneous tokens. But syntax errors, which are just messages, are recorded outside of the syntax tree as side data. Because they're kind of like, they're not really a property of a tree. They are property of a particular parse of a tree. Okay. So yeah, that's like syntax node definition. Yeah, I guess before we look into the parsing, which actually brings the parser into the picture, let's briefly discuss syntax error and pointer. Like syntax error is just like stupidly stupid. So we don't do any fancy syntax errors. It's just like a string and a text range, and that's it. Someday we will think about how to express Rust C's rich diagnostics in the syntax layer, but not today. The second thing is pointer. I think we've briefly covered this in Rowan, but it makes sense to reiterate here because it's like a really important data structure. The overall problem we are solving with syntax pointers is that we do not want to keep all the syntax trees in memory all the time. So imagine you are working in a project in an IDE, and like this project contains libraries. You don't really want to keep the source code as a parse syntax tree for the libraries in memory, because that would occupy a lot of memory. Full fidelity syntax tree, which contains all the whitespace, all the comments, is pretty intensive in terms of memory usage. That said, so yeah, for example, we don't want to have a syntax tree for the hash.res file from standard library in memory all the time. That said, when you actually go to definition to this file, well, you kind of like want to have all IDE features here. You want to have completion. You also want to have syntax highlighting, go to definition, whatever. So at this point, you need to parse this back in the syntax tree. That said, once you close this file, you probably want the syntax tree to go away because we no longer need it. We only need like the signature of this file, like the number of functions, their parameters, but we are not interested in their bodies. So this creates this environment where syntax trees are transit. They come and go, and you only get a syntax tree once you really need to use it. But if syntax trees come and go, you cannot just use syntax node to persist this information. So for example, like we don't need the full syntax tree, but we need like some form of a signature of this hash module, and we need to somehow remember that like this hash name actually refers to this syntax node so that we can make go to definition work. And the way we do it is by using syntax pointers. So yes, the trees come and go, and we might reparse this file several times. So we cannot just directly store the syntax node. But what we can do is that we can store a pointer to this node. Roughly, like say, we can store, okay, it doesn't show syntax position, sadly. But anyway, so kind of like we can store, for example, the range of this file, of this node in the file, and say, hey, like this hasher is a node which you find in this file. It's which you find in this file starting at like this offset, and which goes for like, why are you not showing how many characters are selected? This is like too many, and you are overflowing. Anyway, so yeah, basically, just remember like the text range in the file. And these pointers, you can actually, like, they are cheap than just basically an integer, and you can store a lot of them, and they are stable across reparsers. So you can use the same pointer with different green trees at different points in time. So let's see how they are implemented, and they are implemented exactly like this. There's like a text range and a syntax kind. And the reason why we need syntax kind is because there might be the cases where two nodes have exactly the same range. So if you look at, I don't know, here, like this path, you see that at the bottom layer we have identifier, and this identifier is wrapped into nameref, and this nameref is wrapped into path segment. So all these three nodes here have exactly the same range, and using only the range isn't enough to disambiguate which node exactly are you talking about. That's why we also add a syntax kind here to say, hey, like, we are looking at the node at this range with this specific kind. This also helps with debugging because, well, when you get a pointer, you at least get an idea of what kind of node are you looking at. I'm not sure that this text range is the best representation, although I'm also not sure that it is the worst. So today, we're using a text range. Another thing you can do here is you can store just the node ID. Basically, you can walk the tree and enumerate all the nodes and say that the syntax pointer is just the node's number. Then, if you store in each node the total number of its transitive children, descendants, then you can actually relatively quickly find the node by its number. That would probably be the most principled representation here. Another interesting trick here is to use a path as a node identifier. Basically, you store ID as a vector of integers, where something like 1, 2, 3, 1 means start at the root, go to the first child of the root, then go to the second child of the root, not of the root of this new node, then go to the third child of this new node, and then go to like the first child of this like final node. So you like, basically iteratively describe how to descend from the root to the node you are looking for. But we are using like the simplest possible thing, just the text range. And kind of like a lesson in software architecture. Originally, that was just pub, because sometimes it actually would be convenient to look at like syntax node text range when you are writing some code further up the stack. And when I was writing this, I really knew that, hey, in the future, I actually will be changing this representation. But while today, like, that's text range and that's convenient, so let's just expose it. And that turned out to be a wrong decision, because by the time when I decided that, hey, I actually need to experiment with different representations here, and to actually try out if path would be faster, fixing that turned out to be pretty complicated, because there were usages of this range all over the place. So yeah, if kind of like you think that, hey, I'm going to keep this public temporarily, and then I will switch it to private in the future, that's always a wrong decision, because, well, switching it to private in the future is going to be a giant pain. So better start private. Okay, so first of all, how do you get a syntax node pointer? You start with a syntax node and recall its text and its kind. And then how do you resolve pointer? Well, let's see. You start with the root node, and then you iteratively deepen into this root node, looking for a node with a specific text range. So you repeatedly take the current node, look at its children, and find the one with a specific range. Yeah, and among these iteratively deepened nodes, you actually want to find the one with specific range and specific kind. And if you recall, this child looking at range actually bottoms out, like here we are inside the Rowan already, bottoms out in a binary search of a list of children by the text range. And that's why, again, if we go all the way back to green child, yeah, And this goes all the way back to the fact that when we store green children, we store relative offsets of these children. So that allows us to use this binary search here, because if we didn't store relative offsets of the children, then finding a child which overlaps the given text range would incur a linear scan. And that goes to like this to-node function Rust analyzer. And this to-node is actually very hot. A lot of code does this green pointer, syntax tree pointer manipulation, syntax tree pointer dereferencing. So before we implemented this binary search, we had a pretty horrible, accidentally quadratic performance cliffs all over the place due to the fact that we did linear scan here. The IST pointer talks about IST nodes, and this will be covered probably in the next video. But kind of like as a foreshadowing, if you remember, when we were writing mini Rowan, we ended up writing. We started with a raw untyped API, and then we wrote a tiny typed IST wrapper on top of it. So like that's IST-ptr is pointer to those typed wrappers, which we will be covering separately. Okay. That is the basics, I think. Finally, let's go to the Parser. So parse text. It takes a string of text as an input, returns a parsed syntax node and a collection of syntax errors. So like that's very simple. And again, I kind of like the simplicity of this API. It like does exactly what it promises, and it doesn't have any kind of like hidden external state, because that's actually like the fun thing about Rust is that Rust-C. In Rust-C you sometimes also see like these kinds of functions, but there is like all kind of like implicit context everywhere, which is like hard to follow. Here this is like really simple. It's like a pure function. You take a text, you get a syntax node back. So first of all, we need to split the text into tokens, specifically into Lexer tokens. As a reminder, in Lexer, something like this is represented as a pair of tokens without white space between them. That is the tokenize function, which is not that hard. So for tokenization, we actually use the same Lexer which is used by Rust-C, or rather, I should say, we use the Lexer which was extracted from Rust-C specifically to be reused between Rust Analyzer and Rust-C. It would be impossible to use Rust-C Lexer as is, because, well, it used to be like this giant mass of global state, but it was possible to extract out of it a thing with a simple interface, which we actually can use. And again, kind of like the thing with state is still in Rust-C. It's that it's just like split into the pure thing, which just the lexeme itself, the essence of Lexer, and then a stateful thing which assigns spans, internal identifiers, and all that stuff. Yeah. So like this Rust-C Lexer thing returns a vector of tokens, where tokens are really simple. They are a pair of kind, and kind is just like fieldless enum. I lied. It's not really a fieldless enum, but like conceptually it is a fieldless enum, because like things like comments and I think strings. Oh yeah. Strings are in literals, are a little bit more complicated. But yeah, still, like these literal kinds do not contain evaluated tokens. So an int isn't represented like an integer. An int is represented like basically like a bunch of offsets into the actual raw string. So these tokens are conceptually just a string with some annotations. They are not values of tokens. Okay, so we got a bunch of those tokens. And we want to convert them into our own tokens. And in our own tokens, the representation is even simpler. Here, the kind of token is literally this like fieldless enum syntax kind. And that mostly boils down to just translating from whatever token kind we got from Resync to like the token kind we had here. So kind of like if you get semi, you get semicolon. If you get comma, you get comma. And let's, yeah. And if you get a literal, then it's like a little bit harder. And those enums contain some information about error, so that's also recalled here. So as a result, tokenize basically splits the text into tokens and gives us a bunch of syntax errors. Okay. Then we need to feed these tokens into our parser. If you recall, parser is abstracted from both the syntax tree and the source of tokens via this source sync traits. So we have this text token source for text. It contains the original text, it contains the list of tokens, and each token also remembers its offset in the text. And it contains the current position in this string. So when we want to look at the current token, we just look at the current token. When we want to do a look ahead, we just do a look ahead, and again, that's like not a super difficult logic. You have like this slice of tokens, you get the one with the correct offset, and then you return the result. But that's actually interesting. This is not something I've covered when I was describing parser, but which something I should have covered. Basically, when you're writing a parser, one of the conditions you need to handle is the end of input. And when you code this code naively, end of input is like a separate condition. But when you parse in something, you generally like expect to see a particular token. You want like to see, say, a semicolon. And you don't want to write everywhere, hey, if the token I got isn't a semicolon, or if I haven't got any of a token because it's in the file, you want that to be just one condition all the time. And that's why it's useful to introduce an explicit token for end of file. So that conceptually the stream of tokens you feed into the parser is infinite, and but it's just like padded with those end of file tokens at the ends. So you don't need to return options from look ahead. You always get like this token, but which might be an end of file token. Okay. So yeah, if to bump a token, we checked if we reached in the file, and otherwise we just like increase our position by 1. How does it work? Oh, right, like this is like this position. And if we want to, and like, yeah, like, that's probably like the hardest bit here, like checking if like the current token is a specific keyword. So here we need to fetch a text of token. So we get the current token, we look at its offset, and we look at if the string of this token is a specific keyword. Note that we could have added a generic function to just get the text of a token, so that the parser, so that we don't have to special case with is keyword and let the parser just like to compare text by quality. But I don't think it's a great idea, because we want to make the interface is as restricted as possible, and we do want to basically allow the parser to check only for contextual keyword and not for arbitrary text. So yeah, that's like the token source for you. The next thing is text resync, and again, it's like slightly more involved, but the general idea is the same. So we have all this contextual information, the text, the tokens, current position in text, current position in tokens, the state, which I don't really remember why we need this. Okay, yeah, it's kind of like ironic that I like look at the piece of code and complain that I don't understand what it is doing, and the blame says that I offered this code 3 years ago while apparently adding documentation, and there isn't documentation here. Yeah, well, there is documentation here, like state text resync. Yeah, okay. I guess we would have to like understand what is this doing. Okay, so as a reminder, the tree-sync should support starting syntax nodes, finishing syntax node, emitting errors, and emitting tokens. So let's see how we emit the tokens. As a reminder, when we emit tokens, we want to glue this into this. So this method tells us, this argument tells us how many raw tokens should we consume. This trivias is interesting. We will cover it slightly later. But here we see, hey, we just kind of like take all the tokens, compute their total length, and call some internal methods, which apparently like does the actual glue. And yeah, that's exactly what happens here. So we look at the raw text, and emit a token with a specific kind of this glue text internally, and that we'll call green builder into the inside the Rowan, which will try to look this token into the cache of tokens, because well, green trees all have like this structural sharing, and if it is not found, it will actually allocate this new green token, blah 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 blah. So yeah, you see, like I wasn't like tricking you. It really is like this like whole stack of things which bottom out in Rowan. Okay. Starting node. So again, you see there's like this a lot of code about this trivia, which I am not talking about, but the rest is pretty straightforward. So we yeah, I don't really understand what like state is doing, because actually I would expect this to be just like start the node and then in finish the node, like finish the node. I guess, yeah, I guess, well, why do we need this? State. Yeah, I guess, yeah, I guess like the state is also like a part of this confusing thing with trivia. So yeah, but like in a nutshell, we just like proxy from text resync to Rowan green builder. So what's the deal with the trivias? Why we need it here? Yeah. When we write a parser, we actually do not want to care about comments and whitespace. We do not want to write an explicit code for skipping whitespace inside the parser. That said, when we produce a Rowan syntax tree, we absolutely do care about whitespace and comments, and we want them to be present in the syntax tree. And the way we do this is that we actually just hide these trivia tokens from the parser, and in the layer of and so like the parser tells us what like significant nodes constitute our syntax tree. And in this tree sync thing, we just see what are the trivias between two nodes and attach them to the relevant node. And that's actually interesting, because let's look at the example. That's actually interesting, because here, like intuitively, you would want this comment to sort of like be the part of this function, because it like feels like a function level comment. But because there is a blank line here, you probably don't want to treat this comment as part of this function. Like this comment feels like it is attached to the module. So it's kind of like non-trivial. And you see that's exactly what happens in the syntax tree. So the comment gets attached to the function, and this comment gets attached to the source file. You actually can see this using extend selection. So if we press extend selection on the function, at one step we extend this selection to this comment. And at the next step we extend it to like the whole thing. If you remove this blank line, then both lines get attached to the function. So yeah. I guess actually that means that we've glossed over one specific bit in the text token source, which is interesting. How do we create it? Yeah, so that's like that's an interesting bit. The interesting bit here is that when we get the tokens from the lecture, we get them with whitespace and comments. But here, we actually store non-trivia tokens. And this filter map is what we're doing here. Is where we're doing this. We check if the kind is trivia, and trivia is defined as whitespace and comment. And we only store this token in a text token source if it's not trivia. Okay. So how do we now actually, after we've hidden the trivia from the tokens, how we actually restore them back into the syntax node? Well, and that's like the it trivias method. Probably like this. Yeah, okay. Yeah, it's pretty complicated. I'm not sure I will be able to like just quickly explain how it works, but where is like the case? Okay. Yeah, but I guess that's like the core idea here, like this method, and attached trivias. Basically, so you kind of like produce the syntax nodes, and you are at a moment where you need to like emit the final node. What you want to do at this point is to determine how much white space, how much trivia you want to attach to this node, and how much of the trivia you want to attach to the parent node. Again, in the example, like with these comments, when we parse this fn attach and attach trivias function, we have like a bunch of trivias here. We have like this white space, we have this comment, we have this white space, we have this comment, and we have this white space. So we need to determine that we want to attach one comment and white space to this node and leave the rest of the comments and white space to the parent node. And that's exactly what this function is doing. It takes the syntax node we are producing. It takes an iterator of trivias, and here it tries to like smartly look for blank lines, for doc comments, and use that information to figure out what is the position where we should cut the trivias. Once you get that position, you can actually okay, yeah. So that's, yeah, okay, yeah. So now it is much more clear. So basically let's split the screen in two so that it's easier what we are doing. Okay, so we are looking at this code, and let's think about this example. So let's say that we want to start this function now. At the moment, like our position is here, and we know that we want to start like this node. And the question is like, where do we cut this syntax of this sequence of trivias which is ahead of us? Because we want to cut it at this position. We used unattached trivias to determine this cut point. Then we eat the trivias before the cut point, attaching them to the parent node. Then we start a real node, and then we add the rest of trivias and attach them to the just started node. So I hope this makes some sense. But yeah, this trivia attaching idea that you can do this outside of a parser in like semi-intelligent way is actually one good thing to take out of this video. Yeah. So started with text, converted it to tokens, converted tokens to token source, where we hide all trivia tokens, then set up a resync to actually restore these trivia tokens back. Then finally, we call this parsers file from the parser module which we looked at last time. This will consume the token source and populate the resync with the actual syntax tree. Then we get the actual syntax tree from the resync, and again, by the time that parser finished, we actually might be having some leftover trivia, so we need to eat them. We also get the accumulated syntax errors, we add lexer errors to them, and we recall parse tree and a bunch of errors. So yeah, that's it. Hopefully now, like the last like 5 or so videos start to make sense, because yeah, that's the place, like that's the entry point where we tie everything else together and go from the raw text to the actual syntax tree. Go from like these symbols to this nice tree structure on the right, which represents every bit exactly. Thanks for watching, and see you next time when we will be discussing IST and code generation for this IST. Goodbye.